Good morning, afternoon, or evening. Welcome back to our third to last lesson in our trigonometric journey, where we are going to utilize the relationship between arc length and radian angle measurements to calculate distance traveled around a circle so we can create trigonometric functions to model circular motion. First up, we have four different graphs, and as you can see, we've adjusted the input in three of those graphs. So it should be relatively straightforward in terms of defining which one of these should not belong. Remember, there is a specific reason as to why each of them do not belong. So there's not necessarily a wrong selection as much as there is an invalid justification. So something we've been talking about for the past few lessons is identifying the period of a trigonometric function. Graphically, it's always more convenient than algebraically because we can kind of use the shape of the graph. But if you've forgotten, the period is the distance between the maximum or minimum value and the midline of a trigonometric function. Now, as you can see, we have the algebraic representation of a few different trigonometric functions based on these situations here. Use your intuitive sense to see now that there is a scale factor attached to the input of the function. Is the period necessarily going to alter, since this is something we've discussed before in identifying the period with a different type of algebraic structure? What is the period of the function y equals cosine pi of theta? And then identify a possible equation for the graph provided here. Okay. Things that we want to think about, we can see that the graph with an input of 0 is starting at 1. At 1, and this is on a theta angle of rotation. So when theta is 1, we also have yet another maximum of 1, minimums at 3/2 and 2/4. We're not saying pi. Okay, we're looking at theta as numerical values. And then we get to the most important part. So the world's tallest Ferris wheel is located in Las Vegas. It is absolutely massive and stunning to see at the same time. I unfortunately did not have an opportunity to ride on it, but this is the function that models the behavior. And we can take each of these components to represent a particular aspect of the Ferris wheel. The diameter of the Ferris wheel we know is double the radii. And looking at this function, we should be able to identify the radii. We've been provided the sine function because remember, sine, it represents the vertical distance from the center of the circular object. One thing we haven't talked about yet is the time span that a scale factor provides regarding circular motion. So looking at 2 pi t over theta, we want to think about, in order to complete one cycle or one rotation around a circle, it takes 2 pi radian. So what numerical value can we substitute for t that would represent time? That would ultimately simplify this entire expression here, 2 pi t divided by 30 to 2 pi, right? So we're looking for the corresponding point that would represent the location of 2 pi radian. It should be rather intuitive, and if it's not, let's discuss that in class. Give at least 3 different times when the passenger seat modeled by F is at its lowest point. Explain how you know. You might think, well, there's only one time it's at its lowest point, but remember, a Ferris wheel is circular, so that just means you continue rotating and you're back there a predetermined amount of time later. Think about the corresponding point on the unit circle in which we have our lowest point, which is typically for sine, not typically, but always 3 pi over 2. That would not be the same coordinate here or same input here, simply because we have we have the sine function transformed with all these modifications attached to it. And then sketch a graph of the height of the seat on the Ferris wheel for at least 2 full revolutions. Okay, so the question becomes, how long is it for 1 full revolution? And then we can double it. The scale, I have adjusted your scales here to take that into consideration. And that's where we're going to pause. So at this point, we've been working on this content for quite some time. So this is starting to put a bow on all of the concepts and characteristics of trigonometric functions. If you are struggling to interpret this function, you must advocate, participate, and I can't remember the last one. But advocate, participate, and let's go with engage during our class debrief. That's where I'm going to pause you, and we will pick up in class.